Does it show recording somewhere? Yeah, yes, I guess. Yeah, you can start. Go ahead.
All right, ladies and gentlemen, welcome to the 18th seminar provided to you by Kurdish Mathematical Society. Due to some technical issues, we couldn't deliver the seminar last week, but thanks to Professor Fernandez that took his time and is willing to do all of this again. We really appreciate it. Once again, it's an honor to hear this amazing talk, of course, by a genius mathematician like you, sir. So we're happy and we're very excited to have your talk, and very welcome to all our participants for joining us again. The instruction would be just as last week. Everybody would stay muted up until the end of the seminar, in which anybody who has got a question could raise your hand. I think you could raise your hand, and we would then require you to ask your question, and then all your questions would be answered, and that's it. Now the stage is all yours, Professor. You could go ahead.
Thank you very much, and thank you for being patient with my university's technical issues and being able to reschedule this presentation. I'm glad that I'm now getting the chance to give it, hopefully without any connection problems. So once again, welcome, or rather welcome back to the participants. I'm going to, for the sake of the recording and perhaps people who joined only this time, I'm still going to go through the early slides of the talk, but I may try to go a little more quickly through those, and then I can have more time to talk about the later parts. So my talk is about fractional calculus, and I'm going to give an introduction to this topic from various viewpoints, including pure mathematical, applications viewpoint, differential equations, and here is the outline. I'm going to give the motivation, the history of this topic, some basic definitions of the operators of fractional calculus, and then many varieties, different types of operators that have been defined, which is also the main focus of sections 3 and 4, talking about various different types of fractional calculus, how they connect with each other, how they can be generalized. Section 2 is also interesting from the viewpoint of differential equations, how there are problems with specifying initial conditions that only appear in the fractional scenario. So there are new issues, new problems to be resolved in fractional calculus specifically. So here is the basic idea. What is fractional calculus? It's about giving meaning to non-integer orders of differentiation and integration. In classical calculus, we learn about derivatives and integrals to integer orders, where the fundamental theorem of calculus gives negative integers, but fractional calculus allows us to extend to rational, real, and even complex orders of differentiation and integration. By the way, the word fractional is not technically correct in a way, because the orders are not only fractions, but they can be in other spaces, but this term has just kind of stuck, and it's the term that people use. As we will see, there are many different types of fractional derivatives, not a unique definition. And I also want to mention the word differintegration, which includes both differentiation and integration. Let me motivate this topic firstly. From the applications viewpoint, with the caveats that I'm a pure mathematician, so applications is not my expertise. I'm just going to talk about this up to the level that I know and no further. So one of the advantages of fractional derivatives is that they are non-local, which means they can be useful in modeling real-world processes with, for example, a memory effect, which would be non-local interactions in time, or some process involving non-local interactions in space. We also have the concept of viscoelasticity. So a viscoelastic substance is somehow between a liquid and a solid. So liquids can have viscosity, solids can have elasticity. And if you have a substance that is in between, or it has somehow properties of both, then it makes sense to model the behavior of this substance by differential equations with orders between one integer and another, i.e. fractional orders. My favorite example of a viscoelastic substance is the glue that holds, for example, stickers. So if we have a sticker and you want to, it's stuck to some paper or jar or whatever, and you want to peel it off, then what often happens is if you peel it slowly, then the glue that is holding it on acts like a liquid, like a fluid. This glue is flowing, and therefore slowly you can pull the sticker off. But if you try to pull it quickly, then the glue acts like a solid and it just tears and breaks. So this glue is an example of a viscoelastic substance and a way that you can see sort of fractional calculus in everyday life. There are many applications in the literature. Again, there is a caveat here that there are both good and bad applications, in the sense that some claimed applications really have no evidence for connecting the real world model, the real world phenomenon they're trying to model, with fractional calculus. So sometimes people take a differential equation that models something and they simply replace, they substitute, instead of a classical derivative, a fractional derivative, and they say this is a fractional model of the same thing, which of course it's not, because fractional derivatives have different behaviors. The model is not going to behave in the same way anymore. Maybe it's not going to fit. If you want to create a model, you need some kind of evidence that it is a reasonable model, which often does exist. So I'm not saying that all the applications are bad, just that one must be careful with these papers to distinguish between the good ones and the bad ones. There are a lot of real serious applications of fractional calculus with real world data, sometimes even showing that the fractional model fits better than the classical model, which is then a big advantage of using these operators. From the mathematical viewpoint, fractional derivatives are a natural generalization. For me, this was a question that occurred to me when I first learned calculus. We also discover new behaviors. So this is always interesting in mathematics when we generalize some specific concept to a more general one, which behaviors stay the same and which ones are different. For example, ordinary derivatives and fractional derivatives are both linear, but ordinary derivatives are local operators and fractional derivatives are non-local operators. The Leibniz rule or product rule is a nice example of a situation where fractional derivatives behave differently from ordinary derivatives, but in a very natural way. If you consider the Leibniz rule for the nth derivative, if you write it down and look at it, I didn't have time to put this on my slides because there's so many different things to discuss. But this is an interesting idea. You write down the Leibniz rule and you consider how would this naturally extend to fractional derivatives. And the guess that you make based on the binomial theorem is actually the fractional Leibniz rule. So the differences sometimes are natural and expected. New challenges, for example, maybe you have a method, a well-known method perhaps, to solve differential equations. You want to extend it to fractional differential equations. Sometimes this is trivial, and there is nothing interesting in extending something that just works in exactly the same way. Where we find interesting mathematics is where the new problem cannot be solved in exactly the same way, but some new challenge requires a modified method or a workaround or something slightly different from the classical scenario, and this is where we can really get some new mathematics. The history of fractional calculus starts in 1695. This is a date that everyone in this field of research is always quoting, 30th of September 1695, the letter from Leibniz to L'Hôpital. So L'Hôpital asked, they were talking about derivatives, the order of derivatives. L'Hôpital asked, what if the order is 1/2? And Leibniz said, it appears that one day useful consequences will be drawn from these paradoxes because there are hardly any paradoxes without usefulness. This was the comment of Leibniz. Just a comment, a philosophical statement. He didn't really develop it mathematically, but it's interesting to know that the idea goes back to the beginning of calculus with Leibniz himself. Up until the mid-20th century, the field developed very slowly. Some big names of mathematics, for example, Euler, Riemann, Abel, Liouville, Hardy, Littlewood, they looked briefly at fractional calculus. They wrote some small things about it, but not more than a few papers, let's say. The first application was from Abel, solving the tautochrome problem from classical dynamics, formulating the problem in terms of integrals to order 1/2, solving it using derivatives to order 1/2. There was an interesting dispute in the 19th century, which has parallels in disputes in this field today, between people who proposed different definitions of fractional derivatives that were not compatible with each other. So Lacroix had a formula that was very natural for power functions. Liouville had a formula that was very natural for exponential functions, but they were not consistent. They could not both be true at the same time. And so they argued about which one was better to use, because power functions lead to Taylor series, exponential functions lead to Fourier series. Both of these types of functions generate many, many other functions. And it was De Morgan who said both these systems may very possibly be parts of a more general system. As we shall see later today, De Morgan was correct. Since the late 20th century, this field has developed very rapidly, and we have many new operators, generalized operators, some of which I will talk about today. 1974 was an important year for fractional calculus, the first textbook devoted to this topic only, the first conference devoted to this topic only. I also mentioned several other textbooks here. The reference number 2, Samko Kilbes-Merichev. This is an enormous book. It's a good reference text. It does basically everything from the pure mathematics viewpoint. When they say theory and applications, it means applications within mathematics. There is nothing in this book about real-world applications, but for example, Miller and Ross has real-world applications, and these other books, at least they say something about the applications of the topic. Oldham and Spanier, the first book, was even a collaboration between a mathematician and a chemist. Okay, let's come to the basic definition. So we start with the following fact about nth integrals. So if you integrate a function n times, that means integrate starting from 0 up to x, then the result of those n integrations is convolution with a power function. More generally, we can go from c up to x, a general constant c, but the same constant every time. We integrate n times the function f, and we get this expression on the right-hand side. Now, the left-hand side cannot easily be extended to fractional n. What does it mean to integrate 2.5 times or pi times? It doesn't have any meaning. But the expression on the right-hand side can be easily extended to the case where n is not an integer, and this gives us the Riemann-Liouville fractional integral, which is here. C is a constant of integration. If c equals 0, we get this nice convolutional formula. H alpha would be a fractional power function, and the convolution of f with h alpha is precisely the Riemann-Liouville integral of f, starting from 0. Assuming c is finite, the space of locally L1 functions is enough for this to be well defined, or of course, any subspace of that will also be well defined. And this expression is analytic. So as a function of alpha, this is important. Oops, sorry. So alpha now is a variable. It can be a complex variable. And we can consider how this whole expression depends on alpha. 1 over gamma is an entire function. With alpha in the exponent, it's an entire function. So as long as the integral is well defined, which is for alpha positive or real part of alpha positive, it depends analytically on alpha. So we have a function of alpha, complex variable, which is well defined and analytic on the right half plane. A natural question is, can we extend this to the entire complex plane? And the answer is yes. This analytic continuation is called the Riemann-Liouville fractional derivative, and it is defined in this way. So this expression is the definition of fractional derivatives when alpha is positive, or real part of alpha non-negative. And if alpha is negative, then this reduces to the fractional integral that was already defined, namely derivative to order alpha is the integral to order minus alpha. So that means both of these expressions can be defined on the entire complex plane. So the integral to a positive order is defined by this expression. The integral to a negative order is the derivative to a positive order, which would be defined by this expression. So you can define the integral to any order, left and right half planes, and of course the same for the derivative. Of course, for the Riemann-Liouville fractional derivative, we need a smaller function space. We need some differentiability conditions. For example, f absolutely continuous to order n is a sufficient condition. Not necessary, but sufficient. What is n? So this small n here I've written is greater than or equal to the floor of real part of alpha plus 1, and it must be a natural number. Now, in fact, any natural number n satisfying these two conditions will give exactly the same thing on the left-hand side. So in some sense, we have freedom of choice for n. Usually, we take the simple choice of n, which is the floor of the real part of alpha plus 1. So it says greater than or equal to. Let's just take that, because that is a natural number. If alpha is restricted to be real, then we can also choose n to be the ceiling of alpha. But if alpha is complex, then the ceiling of the real part of alpha will not be good enough. For more details about the analytic continuation and about how to define n in terms of alpha, I refer to this recent conference paper of mine. These facts are well known to experts in the field, so I was not doing anything new in this conference paper, but apparently not well enough known to even reviewers and editors who were rejecting my papers because I used analytic continuation. So I thought it's good to make everyone in the field aware of this, to explain it in detail, to show exactly how it works with all the floors and ceilings and all these details. So that's now a nice reference point for perhaps beginners in the field to get familiar with these concepts. So let's quickly justify the definition. There is also the question of why do we have an arbitrary c? So this arbitrary constant of integration is now extended to a constant of differentiation as well, which seems strange. In classical calculus, you don't have a constant of differentiation. But now we have this constant of differintegration. The reason is that if c is 0, we get a very natural formula for power functions. If c is minus infinity, we get a very natural formula for exponential functions. These two facts, they are easy to prove using definitions of the gamma and beta functions. And this means that De Morgan, in the end, was right, because Lacroix and Liouville were arguing with each other, but both of their definitions were parts of a more general system, which is what we now call Riemann-Liouville fractional calculus. It was not a collaboration between Riemann and Liouville. It came out actually later than both Riemann and Liouville, but somehow people call it Riemann-Liouville. That's another misnomer in this field. Anyway, this Riemann-Liouville fractional calculus includes both Lacroix's definition and Liouville's definition, and therefore we see why it's important to keep the constant c as arbitrary, instead of saying, here is one fixed choice of c. Well, different choices make sense in different contexts, according to, for example, whether you're interested in Taylor series or Fourier series, Laplace transforms or Fourier transforms, initial value problems or boundary value problems, and so on. So basic properties of fractional calculus. I already mentioned the operators are linear. We have a semigroup property for fractional integrals, but we do not have a semigroup property for fractional derivatives. Fractional derivatives are non-local because they're defined in terms of fractional integrals. In classical calculus, of course, integrals are non-local, derivatives are local. And the most common question that people ask when they first hear about fractional calculus is there a geometrical interpretation? We know that first derivatives describe steepness, second derivatives describe convexity. What about the half derivative or 1.5 derivative? The short answer is no. There is no simple geometrical interpretation. The closest thing we have is this work of Igor Podlubny about shadows on the walls. So he is one of the experts in this topic. He also wrote one of the textbooks that I mentioned earlier, and he's an excellent speaker, and he's given a couple of talks about the history of fractional calculus, history, applications, interpretation, which are available online. So I encourage people to go and look up his talks if you want to learn more about those aspects. Now, in the discussion so far, we have defined nth order derivatives and nth order integrals. For n, not only integer, but any real number, any complex number. So it seems like we've answered this question, but we've only given one possible answer. And there are many different possible answers, many different operators that can be called fractional integrals or fractional derivatives. So one important example is the Caputo derivative. So let's just remind ourselves the comparison, the Riemann-Liouville derivative. We have the nth derivative of the fractional integral. Now, with Caputo, we have the fractional integral of the nth derivative. Exactly the same n, the same two operators here, but in the other order. So this is not equivalent to Riemann-Liouville. Those two operators do not commute. And the most important difference is in initial conditions. I won't talk much about this now because I have a whole section about it later. So I'll come back to this. But Caputo is basically another way to define a fractional power of d by dx, a fractional power of the simple first order derivative. But sometimes in differential equations, in applications, we may be interested in other first order operators. Can we define a fractional power of this or that? Can we define fractional powers of the second derivative? And so on. Can we replace the kernel? Remember this h alpha, the fractional power function, it can be replaced by other possible kernel functions depending on non-integer parameters, which you can think of as fractional orders. Is there a classification system? Is there a general fractional derivative or general fractional integral that includes all the different possibilities? Well, not all. We cannot talk about all possible fractional derivatives because there's so many nowadays, and we don't even have a single agreed upon definition for what is a fractional derivative. Different people have proposed different criteria, different definitions, but nobody quite agrees. So the boundaries of the field are not even clear. What is a fractional derivative, what is not? And we don't have something that's general enough to cover all of these, but we definitely have things general enough to cover many of these. So that's what I'm going to talk about in like the third and fourth sections of this talk. For now, I want to mention a few topics that will lead on to the next section on initial conditions. A classical result from any course on differential equations is the Laplace transform of the nth order derivative. This is very useful for solving ODEs, some PDEs. Laplace transform of the nth derivative is s to the power n f hat minus this finite sum. But if you look at the finite sum in bold, I put what is basically an initial value. We have a power of s and a power of dx, so a derivative order and this exponent here. And if you add together the derivative order and the exponent of s, you always get n minus 1 for every term in this sum. So when you go to the alpha order derivative, the fractional derivative, you would expect to have two things that add up to alpha minus 1. Then, of course, one of those two things must be fractional. They cannot both be integers. And it turns out that for the Riemann-Liouville fractional derivative, the s exponent is still an integer. The derivative order is fractional. For the Caputo fractional derivative, the derivative order is an integer. The exponent of s is fractional. So in blue are the initial conditions needed for Riemann-Liouville, which are fractional initial conditions. By the way, if k equals n, the highest value of k, then alpha minus n is actually going to be negative. Therefore, one of these initial conditions is actually a fractional integral, and the others are fractional derivatives. For Caputo in red, the initial conditions are classical type, simply the function f and its ordinary derivatives evaluated at the initial point. Fundamental theorem of calculus, another, well, its name shows that it's very fundamental. How does this work in fractional calculus? You have the nth order nth order integral of an nth order derivative. The formula is this. In bold, we have the same initial conditions as before. Okay, this is n minus k goes from 1 to n. This is k minus 1, k goes from 1 to n. So it's depending on the same set of initial conditions. For Riemann-Liouville, we have fractional initial conditions. For Caputo, we have ordinary initial conditions. So again, the blue things are the same, the red things are the same in both of these slides. Okay, now let me start to talk about initial value problems. Here is an nth order, not fractional, linear ODE. As we know, this needs n initial conditions. Here are the initial conditions, then it will be a well-posed problem. Why? Let's think about why those are the initial conditions that are needed. Okay, we know this is true. We learned this in some basic course on differential equations, but what's the reason? Underlying mathematical reason. One way to see it is by taking Laplace transforms. If you start with this differential equation, apply a Laplace transform to both sides, then these things in bold, that should be a y, not an f, sorry, but these things in bold are exactly the initial values of y and its derivatives. In other words, those initial conditions are exactly what we see. Alternatively, we could integrate the differential equation to turn it into an integral equation. An integral equation which will have a unique fixed point using, well, a unique solution using a Banach fixed point theorem or other fixed point theorems. You can normally show that an integral equation has a unique solution. A differential equation with initial conditions has a unique solution if you choose the right initial conditions. And again, in bold, we get the initial conditions that are exactly those ones. So now we understand why those are the ones we need. Let's consider a fractional differential equation. We use the same arguments, Laplace transform or fundamental theorem, which we have seen in their fractional versions. Laplace transform here, fundamental theorem here. So in blue, we have these Riemann-Liouville fractional initial values. In red, Caputo ordinary initial values. And that means a Riemann-Liouville differential equation needs fractional initial conditions. A Caputo differential equation needs classical initial conditions. Because of this, Caputo has become popular among applied scientists. So I can even say that for applications, Caputo is perhaps more popular than Riemann-Liouville since the 1990s. So the name Caputo is from an Italian physicist, not a mathematician. He wrote this paper in the 1960s. He's still alive, but the proposal of his definition came, I think, in a 1967 paper. And in fact, this was known about earlier. What we now call the Caputo derivative appeared in the work of Liouville and Abel in the 19th century, but the name Caputo has just stuck recently because it became popular since Caputo. And the reason why it's popular is in the real world, if you have a model, it's much easier to understand physically what a condition like this means instead of a condition like this, right? So a fractional initial condition, what's the physical meaning? How do you measure it? Whereas y of 0 equals k, that's something easy to measure and understand. The advantages of Riemann-Liouville, as I said before, it is the analytic continuation. Analytic continuations are unique. So if you think about the viewpoint of complex analysis, Riemann-Liouville is the perhaps only natural extension of the fractional integral. So yeah, this is the historical background that I mentioned. So now we're already seeing that we have these two different definitions, Riemann-Liouville and Caputo, two different fractional derivatives. They both have their advantages and their disadvantages. We cannot conclusively say one of them is better than the other because it depends on your point of view. Mathematically better, physically better, from which viewpoint? Are they parts of some more general system? Let's use De Morgan's philosophy again. Well, they are, but this has not particularly taken off. So we have the Hilfer fractional derivative, which is defined by combining two fractional integrals and one ordinary derivative. So if you set beta equals 0, you have nothing on the outside. It's an ordinary derivative of a fractional integral. It's Riemann-Liouville. You set beta equals 1, you have nothing on the inside. It's a fractional integral of an ordinary derivative. It's Caputo. So this definition interpolates between Riemann-Liouville at beta equals 0 and Caputo at beta equals 1. And you can take beta to be anything in between. So this Hilfer definition includes both. Here is the reference, Hilfer's book in 2000. And it's a book, you will notice, about applications. So he found applications of this derivative, but it's not really become very popular because it actually does not have the advantage of Riemann-Liouville. It's not the analytic continuation. It also does not have the advantage of Caputo. It does not take classical type initial conditions. So there's no analytic continuation, and also it has fractional initial conditions, even more complicated initial conditions than Riemann-Liouville. So it seemed like there was no particular reason to use Hilfer, no particular advantage. It has had a lot of papers about it, but it hasn't really become a big thing, I would say. Now, there is another problem in fractional calculus. So let's consider taking the fractional integral and then letting x go to 0. So we're taking an integral from 0 to x, and then we set x equals 0. Then it's an integral from 0 to 0, which we would think, okay, that must be 0, right? Not right. If you take the fractional integral of x to the power minus alpha, you get a constant function. That constant is non-zero. If you set x to be 0, it's still the same constant. It's not 0. So why is it that the integral from 0 to 0 is not necessarily 0? Well, it all depends on the function space, basically. So if the function f is bounded, near 0, then you can take the limit of this square bracketed expression as x tends to 0. And because of the boundedness, you can then show that this must be 0. But in general, this is not the case. As we see from this function, for example, which is a singular power function, it's not bounded near x equals 0, and we do not have 0 for the fractional integral. If f is smooth near x equals 0, then remember the definition of the Caputo derivative. The Caputo derivative is the fractional integral of the nth derivative of f. So if f is smooth, it means all the nth derivatives of f are bounded, and therefore all the Caputo derivatives are 0 at the initial value. That's already weird, right? All the derivatives must be 0 at x equals 0. That doesn't seem to make sense. Some fractional differential equations, as I mentioned before, of Riemann-Liouville type, they require an initial condition, which is actually a fractional integral. So if these are fixed, if we assume that f is bounded, all the fractional integrals at the initial value are 0, then we don't have a well-posed problem. For example, here's a very simple Riemann-Liouville initial value problem. This is the type of initial condition that's needed. But if you try to solve in a nice function space like this, absolutely continuous functions, it's not well posed because the fractional integral, and this is indeed a fractional integral, even if it looks like a derivative, alpha is between 0 and 1, the fractional integral of an absolutely continuous function y must be 0. So there is no choice in C, there is no free initial condition. If we allow y to have a singularity at the initial value, then everything makes more sense. So we need to use function spaces that do not require continuity or even boundedness on the closed interval. So function spaces are very important. Functions like this, so E is a Mittag-Leffler function, that is an analytic function. But when you multiply it by this fractional power, if beta is between 0 and 1, you have a singularity, and that's something you often need. We need to allow for singularities. So this is a nice function space that is often used in fractional differential equations. The function f1 is continuous on the closed interval, but we multiply by a power function where the power can be negative. So if p is between -1 and 0, then this thing could have a singularity, and you need to allow for functions like that. So this function space is chosen so that everything in there is continuous on the open domain, locally L1 on the whole domain, but it can be discontinuous. It can have a singularity just at the initial value. So let me now move on to more general types of fractional calculus. Many of these fractional operators, specifically integral operators, specifically the so-called time fractional, they're called time fractional because they are in one dimension, so functions of one independent variable. Because in the real world, we live in 3 spatial dimensions, so you would want to consider functions of more than one space variable, but only one dimension of time. Therefore, if it's functions of one independent variable, we often call them time fractional. And many of these are defined by convolution with some kernel function. For example, we've already seen Riemann-Liouville. There are many other examples with different types of kernel functions. Is there a general kernel function that can contain all of these as special cases? There is no single agreed upon answer to this. There are different convolution kernels that have been defined, not only different individual functions, but different general classes. Before I go to the general classes, I want to tell you about Prabhakar fractional calculus. So this was invented in 1971 by Indian mathematician Tilak Raj Prabhakar. This paper is, well, it was difficult to find online because I think the journal maybe doesn't exist anymore, or the journal doesn't have online backlog, but because this paper has got so famous in the fractional calculus community, now people have uploaded it so you can find it. Here is the fractional integral. The fractional derivative was actually not defined by Prabhakar. It came along later, I think 2014, quite a lot later. Prabhakar didn't even know that he was doing fractional calculus. He was solving a singular integral equation. He just defined this operator. Later, people started to call it the Prabhakar fractional integral. Now, these operators have nice properties. So look at the kernel here. This is a Mittag-Leffler function, the capital E, multiplied by some singular power function. This is the analytic continuation with respect to the variable beta. So here beta is on the right half plane, and here using the minus beta to beta switch, we extend beta to the whole complex plane. Alpha still requires real part positive. And we have this nice fundamental theorem of calculus. The derivative of the integral is the original function. We also have a semigroup property, not in one parameter, but in two parameters. So if you put together two Prabhakar integrals with the same alpha and the same delta, then you will add together their values of beta and gamma, both together. So this leads to a whole lot of interesting algebraic properties that are not the topic of this talk, but it's a very powerful and important thing that you have this semigroup property. Tempered fractional calculus. This is something with a lot of applications. It's basically the same as Riemann-Liouville, but with an extra exponential factor, which you think of as tempering the growth. This is particularly useful in random walks, Brownian motion, kind of stochastic stuff, this sort of applications. It's used a lot in that community. Here is the tempered fractional integral, tempered fractional derivatives. Notice the lambda plus d by dx here. We're taking nth powers instead of just d by dx to the power n. We do lambda plus d by dx to the power n. So we will discover that these operators are basically fractional powers of lambda plus d by dx. But that comes later. That will be in the next section. We'll see this tempered again. For now, I want you to think of these just as convolution integrals. So the Prabhakar integral here, convolution of f with this modified Mittag-Leffler function. The tempered fractional integral, convolution of f with this power function multiplied by exponential function. So these are convolutional operators. There's a big theory of convolutional calculus related to, for example, Mikosinski's operational calculus that's used for solving fractional differential equations. Thinking of them as convolutional operators is very useful, but do we need to study all of these different fractional integral operators separately? Riemann-Liouville, Prabhakar, tempered, dozens of others. We don't need to, because a lot of them have a lot of the same properties. When you try to prove things about these operators, you often find that the proofs go in the same way for Prabhakar, for tempered, for all these different things. So when you see proofs going in the same way for different operators, then you think maybe they are all special cases of something more general. Again, the De Morgan philosophy. So there are different types of general kernel functions. I'm going to show you briefly 5 proposed general kernel fractional integral operators. Each of them has some advantages, some disadvantages. I put in bold here the ones that have continued to be used the most since their definition. So Sunnian kernels started by Kochubey in 2011, continued by Luchko in 2021, and going on a lot after that. So there'll be many papers on Sunnian kernels. Analytic kernels defined by me with Azaslan and Balionu in 2019. We later discovered that essentially the same thing had appeared in 2005. And since then, this definition has been used quite a lot. The others, not so much. They were proposed, could be interesting, but people have not done much with them. Here are Sunnian kernels. This is the fractional integral. The fractional derivative is defined using k. Kappa and k are defined to satisfy a Sunnian condition, which means their convolution is always 1. The advantage is that there is a natural inversion relation. This Sunnian condition, this convolutional identity, gives fractional integrals and derivatives satisfying a fundamental theorem of calculus. The disadvantage, look at this equation, look at this integral. Kappa is a function, okay. Is there a fractional order? Is this the integral to order alpha, to order 1/2? How can you put an order into this? It doesn't have an order. It's a function. Kappa is a function, but there is no parameter that can play the role of the order. So that's a big downside. It's a nice general operator. It includes a lot of operators of fractional calculus, but is it itself a fractional integral is something that can be discussed. Analytic kernels, here we have fractional parameters, alpha and beta. The advantage is that we have a series formula. So this function A is assumed to be analytic. That's why we say analytic kernels. It's modified by a fractional power function. So technically the kernel is not analytic, But we start with an analytic function, we generate a kernel, and the analyticity property is very important. Analyticity of A means that this operator can be expressed as a sum of Riemann-Liouville integrals. So anything you've proved for Riemann-Liouville, now you can extend to these more general operators. This includes Prabhakar, tempered, and many others. The disadvantage is that for this in general, there is no natural semigroup property or inversion property. So it's very hard to define the fractional derivative for general A. You can do it in nice special cases like Prabhakar and tempered, but if you take a general analytic function, it's tricky to define the fractional derivative. It doesn't look very natural. Here are these other definitions. Agrawal's definition, similar to the, well, it does have dependence on alpha, but it doesn't have any assumptions about how this thing depends on alpha. So there's a fractional order, but we don't know if there's a semigroup property or a fractional derivative or continuity with respect to alpha, anything like this. But at least it's general enough to include left-sided, right-sided, two-sided operators.
Sorry to interrupt you. You have got 5 minutes left, just to remind you.
Oh, I thought I was supposed to go for 1 hour.
Actually, the last 10 minutes were supposed to go to the questions, but maybe you could.
I'll try to go quickly through. As you can see, I've got quite a lot of slides left, but I'll jump through this section quickly. Right, thank you. So these Agrawal, Schlicker, and Samet, Zhao Luo, they have been proposed, but as I said, not so much has been done with them. I want to mention a few controversial topics before going on to the next section. So non-singular kernels is something that has been argued about a lot in the fractional calculus community. So these are convolutions with a function k that has no singularity. So it's not like the fractional powers that blow up at one endpoint. It's a singular function, a continuous function. Now, the controversy, I think, here comes from two directions. Firstly, we have problems with initial value problems. To make a well-posed initial value problem is difficult with these operators because of the fact that when you set t to be 0, this is necessarily going to just come to 0. But as we've seen already, this can also be a problem with Riemann-Liouville, with any operator with a singular kernel. So we just need to be careful about choosing the right function space. This is not necessarily a bad thing about the operators. It just means be more careful, maybe change the function space, change the type of initial value problems that we consider. Another issue is not about the operators themselves, but simply about some of the people who work with these operators and define these operators. There have been a lot of problems in the community, like people using these operators and writing wrong papers or low quality papers, but that could be a problem with the authors, but not a problem with the operators. So I think people should distinguish the difference between operators that don't make sense and simply bad work done with good operators. So I mentioned here a recent paper of mine looking at these operators with non-singular kernels and doing some serious maths with them and discovering in a way that they're not so problematic as they seem. Let me give you also a couple of examples of operators that are really problematic in themselves. So this is the so-called K fractional integral. Hundreds of papers about this, K variants of different special functions, different operators. Now, this is the K gamma function. And if you make a simple substitution in this integral, like u equals t to the power k, you can very easily show that the K gamma function is just the gamma function multiplied by a constant with this substitution, z over k instead of z. So let's put that into the K fractional integral. You've got this gamma k function out there, do the substitution, and you discover that the K fractional integral is exactly the Riemann-Liouville fractional integral to the order alpha over k, multiplied by a constant. So all the theory of K fractional calculus is trivial. It's the same as Riemann-Liouville fractional calculus. If you want to prove a semigroup property, you can do it in 5 minutes because you know, or 5 seconds because you know the Riemann-Liouville semigroup property. Everything is obvious. There is no new theory here. K fractional calculus is the same as Riemann-Liouville fractional calculus. But people don't care. People are writing papers about this because it's easy, because it was already done. Another example is the so-called conformable derivative. So here is the definition, conformable derivative to order alpha. Now, a simple calculation with limits. So this looks like the classical derivative, right? It's a limit of some difference divided by epsilon. But basic manipulation of limits shows that this equals the ordinary first order derivative multiplied by a fractional power function. So there is no fractional order in this. It's a first order, and then you have a fractional power of t. So again, that means all the theory is trivial because it's the same as classical calculus. If you have a conformable differential equation, well, it's just a first order differential equation, or maybe second order if you have different conformal derivatives inside each other. So therefore, again, everything is trivial, everything can be done. Conformable calculus is just the same as calculus. For example, you want to prove a product rule, there you go, do it in 5 seconds because it is the first order derivative. Okay, so now I want to quickly justify, I'm going to overrun the time, I guess, but I want to at least briefly talk about transmuted fractional calculus, and I want to justify this from differential equations. Let's think about the Cauchy-Euler or Euler-Cauchy differential equation, linear with non-constant coefficients. One way to solve this is by making a substitution for the independent variable. We put x equals e to the power u, then it transforms to a linear constant coefficient ODE. A linear constant coefficient ODE can always be solved easily, and then we get the solution for capital Y as a function of u, that's y composition exponential, and then we substitute again x equals e to the power u to find it as a function of x. So the process is you start from the red ODE, you take composition with the exponential function to get the blue ODE. The blue one can be solved, capital Y can be found in terms of capital H, and then you reverse the substitution by composition with exponential inverse to find lowercase y from lowercase h, which solves the red ODE. Similar thing with the integrating factor method. You have the general first order linear ODE, we multiply by an integrating factor, we transform it to something that's a simple integration problem. So the red one, multiply by mu, it becomes a simple integration. We find capital Y in terms of capital H. What are these things? They are y and h multiplied by mu. So we reverse, we divide by mu to find lowercase y from lowercase h, which solves the red problem. So in both of these cases, we start with a problem, we do some process to get an easier problem, we solve the easier problem, and then we reverse the process. So let me show you this like a picture. So this is what often happens. You have some difficult thing on the bottom, you do a process to go up, you solve it easily, and you do the opposite process to go down again. So this is like algebraic conjugation. We see this in group theory, we see this in linear algebra. And what we need to do this in fractional calculus is the so-called fractional calculus with respect to functions, which is also called psi-fractional calculus. Another topic with a misrepresented history. Most people in this topic, many people think it started in 2017. Many people think it started in the 1970s. Actually started in the 1830s, like many things. And we've got this historical survey. It's accepted. It's going to appear soon that traces the history of this topic from the beginning up to the recent years. So basically, this is about fractional derivatives with respect to a function. Can we define a fractional power of this operator? And one way to do this is by using a commutative square. It turns out that if you start with f of g of x, how to get to f dash of g of x, the best way is to remove the g, composition with g inverse going up, an ordinary derivative, and then composition with g again. So qg, if that's the operator of composition with g, then we have this formula for the derivative with respect to g. If we put that to the nth power, it looks the same, nth derivative with q and q inverse on either side. And then it makes sense to define this for fractional derivatives. So this is called a transmutation relation or conjugation relation. And it's used to define fractional integrals and fractional derivatives of f of x with respect to g of x. So you've got these definitions up there, these transmutation relations down there, which are equivalent to each other. The history I'm going to skip through because I don't have time for that. I will just say that it goes back a lot further. It goes back to the 1830s. It did not start with these guys in 2017 onwards. They just did small modifications of what was already known. We can also generalize this concept of transmutation. So again, I don't think I have time to explain this in detail, but there's a paper of me and my former student from 2022. We defined these general transmuted operators. As particular cases, you get a relation between fractional differ integrals with constant 0 and with arbitrary constant a. You can do a transmutation from one to the other. Left-sided and right-sided fractional differ integrals with respect to functions is a special case. Hadamard fractional calculus gives you fractional powers of x times d by dx. So that's something I mentioned earlier. Weighted fractional calculus, as a special case, we get tempered fractional calculus, which gives you fractional powers of lambda plus d by dx. And weighted with respect to functions, which is like the most general example of this very general framework. It includes Edey-Kober fractional calculus, which a lot of people work on in the pure mathematical fractional community. You can also combine these different ideas together to get even more general things. So Prabhakar and with respect to functions, tempered and with respect to functions, analytic kernels, Sonian kernels, fractional Laplacian, all these different things you can put together and get even more general operators, as has been done in a series of papers up to, very recently, 2024, 2023, and so on. Bibliography I have in many slides. These are textbooks at the beginning. Then we have papers on general kernels. Then the old papers on with respect to functions, starting from Liouville, 1830s, going up to the present, generalizations, and I will leave it there. Thank you for your attention.
Thank you so much, sir, for your wonderful talk. It was really amazing. Now, if the participants have got questions, please raise your hand so that we would unmute you.
I see one raised hand. Yes, go ahead.
We have to unmute him. I'm not sure if I have the... Yeah.
Thank you very much for giving me the time for a question, make some question with the Dr. Arwa. My question is, you presented that the Laplace of Gabuta derivative and Riemann-Liouville derivative, right?
Mm-hmm.
This from the generalized formula of Laplace, you can make a Laplace for Gabuta Gabuta, for Hadamard Gabuta. If
you mean
you can do that again, please.
Catagampola is one of the things I mentioned as, this is an incorrect term because it's just a special case of fractional calculus with respect to functions.
No.
If you need a Laplace transform that works for fractional calculus with respect to functions, for example, Catagampola, then you need a modified Laplace transform, which is, it has been done in a paper of mine, but I don't think I cited it in this presentation. But yes, I've looked at the Laplace transforms with respect to functions. It's a paper of, I think, Fahad, Rahman, and Fernandez from 2020 or 21. Not the classical Laplace transform, but the modified Laplace transform.
Yes. Yes. That my question again, if this is the generalized formula of Laplace, you know that? Use it G and the H. And the F, G and the F. That G you can make it any functions that you want.
That's what I'm telling you. Yes. Yes.
Dependent of the derivative, right?
Yeah.
Which derivative, fractional derivative you use it. Like a Hadamard, you can use a log for this generalized formula.
Yes. Yes.
Like a G, you can use a log, but you know that don't start from 0 because let's make some singular point there.
I'm just opening now the paper of mine about this.
Yes.
So yes, you need to be careful with the initial values. So you may have to start from a different, maybe you start from 1 if you use the logarithm function, for example.
Yes. Yes, I have this paper.
Okay. Yes.
Okay. Yes. Right.
All right.
Yes. Thank you very much.
Thank you.
For your question.
Thank you very much.
Thank you.
Yes.
Please mute yourself. Okay. Now, if anybody else has got a question, could you raise your hand, please? I guess that's it, but let's see if anybody else. Let's wait a bit. I'm going to repeat it once again. If any of you has got a question, could you please raise your hand?
Are they able to unmute themselves, or do you need to unmute them?
I can't, and I think.
Oh, I
Yes,
think
they can.
we can.
They can unmute themselves. Yes.
Okay, yeah. Because
Okay.
maybe with this new software, they didn't see how to raise hands. So if someone has a
correct.
question, they just ask directly.
Yes, all right. So if anybody has got a question, you could ask directly by just unmuting yourself. Thanks for pointing that out, Professor. I guess that's it. Professor, if you want to finish the slides that you left, you can do it, because I think they don't have that much questions. Or we could just end it here.
No, it's okay. I went through them quickly. I can perhaps share the slides with the participants if that's possible. I
Yeah,
guess there will be a
that's no
recording so people can see also the slides I went through quickly.
All right. That's very good. Yes, it's recording and it's probably going to be uploaded, so anybody could see the slides and could stop it and watch it themselves. Thank you so much, Professor, for all your time and your amazing seminar. We were very happy to hear you, and we're once again sorry for all the inconvenience, making you redo the things. Thank you so much for your patience and your time, really.
Thank you very much. Thank you for having me and giving me this opportunity, or even giving me the opportunity twice.
It's
Thank you.
totally our pleasure.
Once again, thank you so much for having you today, Professor Arran. Thank you.
Thank you.
Thank you very much, Professor Arran. Thank you very much.
You.
Yeah, thank you so much, sir. It was wonderful. Thank you for all the participants for staying up until now. It was a very nice seminar, and I hope everybody has enjoyed at least as much as I did. See you in another seminar series. So good night for now.
Thank you.
Bye-bye.
Bye-bye. Thank you.